Okay, hello, Precalc C. Last week, Thursday, Friday, we learned about the Binomial Theorem. There's some homework in the textbook. Thought it was pretty straightforward. Usually I don't even go over this in class, maybe 5 minutes or something like that, 10 minutes. Let's just do a quick 10-minute video or something, going over some select problems from the homework, which I thought was pretty short. Okay, let's go. Number 17 says, use the binomial theorem to expand and simplify the expression. Okay, well, x plus y to the fifth. Okay, well, how do you actually do this? How should you do this? Personally, when the numbers are still so small like this, like 5, I just use Pascal's triangle. So it's not too bad. You probably even just already, like, look, how long did that take me? 15 seconds or something like that. So Pascal's triangle gives you, and go watch the previous video if you don't understand why, the coefficients of the binomial theorem. So yeah, there they are, 1, 5, 10, 10, 5, 1. So I just kind of like know that now. All right, so what's the answer to this? Well, it's just x to the fifth plus 5x to the fourth y plus 10 x cubed y squared plus 10x squared y cubed plus 5x y to the fourth plus y to the fifth. So, alright, there we go. Done. 25. What's 25? Well, okay, it's not particularly much harder problem. X squared plus 5 to the fourth. Well, I have to put a little bit more effort in now because now, this is like kind of A and this is sort of B. So, alright, but looking at the fourth, again, just using Pascal's triangle, the coefficients are going to be 1, 4, 6, 4, 1. So what does that mean? It means it's going to be x squared to the fourth plus, this is me being very careful now, 4x squared cubed 5 plus the next coefficient is going to be 6x squared squared 5 squared plus 4 x squared to the 1, I guess, yeah, times 5 cubed plus 5 to the fourth. Alright, so I'm just using a certain amount of kind of algebraic discipline or something to write this out kind of very carefully with parentheses, but really I'm just doing the basic binomial theorem where A is x squared and B is 5. So I don't think there's anything really to say about that. So now I can just clean this up a little bit. What do I get here? Ugh, this marker's worse. X squared to the fourth, so that's going to be x to the eighth. X to the eighth plus, now I'm going to get 20x to the sixth plus 25 times 6 is 150, so that's 150 x to the fourth plus that's 125 times 4, so that's 500 x squared plus 625. So that's that. Okay, 39. What's up with 39? Is this just kind of more of the same? Basically the same. Maybe we don't even need to do this. Expand the binomial using Pascal's triangle to determine the coefficients. Okay, I guess we can just do it. 3 minus 2z to the fourth. What is this going to be? This is just the exact same thing over again, perhaps with just more annoying numbers and there's negatives involved and stuff. So I don't know. It's going to be 3 to the fourth. Minus 4 times 3 cubed 2z plus, I guess if you want to, you can think of it as just all being plus. I mean, maybe that's kind of better or something to just think of 3 minus 2z as really just being 3 plus negative 2z. I don't know if you like that better or worse. I think I like that worse. But anyway, too late. So this is like a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed, and finally plus b to the fourth. So this is just how you use the binomial theorem. So okay, what do we get here? We get 81. This will become minus, these are just like big numbers now, so I'm sad. 27 times 8, I don't know what that is. 6, is that just 216? 216z, hold on, is that right? 8 times 3 cubes, that's 2 cubed, 3 cubes, that's 6 cubes, that's 216, sure. And then these numbers are just getting bigger and bigger. That's 4 times 24 times 9. Oh man. 27 times, is that just the same thing? Is that just also 216? 9 times 6, 54 times 4, yeah. So that's plus 216z squared. Okay, and then this is going to be minus 832 times 3, so that's 96z cubed, and that's going to be plus 16z to the fourth. Okay, so some arithmetic struggles there, but I think that's all right. Okay, 43 is now less work to do because now they're saying, all right, don't actually just expand this whole thing. That's kind of silly. Just let's come in and get the term that I want. This is a kind of more now of a real problem. X minus 2y to the 10th. So when you expand out x minus 2y to the 10th, what are you going to get? You're going to get a bunch of things, but what I want to know right now is what is the coefficient of the term which is x to the 8th y squared. So maybe I'll just write that like over here or something. X to the 8th y squared. Okay, well, how are you going to get an x to the 8th y squared term anyway? The only way that's going to happen is by taking x 8 times and taking negative 2y 2 times. And so what I'm doing is I'm just kind of like fake expanding this out. I'm expanding it out, but I'm only looking at the sort of particular term that I'm interested in. But it's really just it's just an extension of what I did above. Well, okay, what is this coefficient now? Okay, this is now it's like embarrassing somehow if you use Pascal's triangle because that's just silly. This is a very large number. Can I just tell you what this binomial coefficient is going to be? Yes, I can. The binomial theorem says that that this is going to be 10 choose 2. And that's because I expanded this tree out to sort of 10 levels deep, and I'm counting the number of terms of the form a to the 8th b squared, and the answer is, of the 10 passed through the tree, I'm counting the number of paths in which I went right 2 out of those 10 times, and there are 10 choose 2 ways to do that. Okay, what is 10 choose 2? It's a pretty small number. It's 10 factorial over 8 factorial 2 factorial. And that's going to be just 10 times 9 over 2. So this is, well, maybe I'll just write this out. So this is x to the 8th, then negative dies times 4y squared. And so what do we get? What did I say that was? 45, right? 10 times 9 over 2, 45. So I get 45 times 4, that's just 180. And so I think the answer to this problem hopefully is 180 x to the 8th y squared. And so that's what you're supposed to do. Yeah. Okay, 45 is basically just the same thing. Just kind of like another one. So 3x minus 2y to the, 45, 3x minus 2y to the 9th, yeah. And so we got a little dot 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 plus, and now I want to know what is the coefficient of the x to the 6th y squared term. Well, the only way for me to get x to the 6th y squared? Sorry, I'm just all over the place. X to the 4th y to the 5th. X to the 4th y to the 5th. Okay, well, the only way for that to happen is if I choose 3x 4 times, and I choose negative 2y 5 times, and how many terms like that are there? Answer, 9 choose 5. And now I just have to work out what this is. So what is it? What is 9 choose 5? It's 9 factorial over 5 factorial 4 factorial. So that's going to be 9 times 8 times 7 times 6 over 4 times 3 times 2. So that's going to be 9 times 7 times 2. So that's 112, I think. 63 times 2 is 106. No, 126. Oh my god. 126. Let me just double check that. 6 gives a 2. 2 times 2. Yeah, 63 times 2 is 126. Okay, so this is 126 times 81 times negative 32. So okay, I've just decided that I'm not going to do this by hand, of course. So if you have a calculator with you, then or a computer or whatever, then you can finish this off. But for me, I'm just going to leave it as the answer is negative 126 times 81 times 32. Whatever that is the coefficient of this problem. This is pretty easy homework. All right, last thing. Let's take a look at this number 67. This was a kind of interesting problem, and there are sort of two ways to do this. There's a kind of a mindless way, which terminates in no understanding, and then there's kind of a cool, deep way. So let's do both. Yeah. Good. What does the exact problem say? It says, prove, this is number 67, prove that the sum of the numbers in the nth row of Pascal's triangle is 2 to the n. Prove that the sum of the numbers in the nth row of Pascal's triangle is 2 to the n. Okay, and this is something that you just sort of can't help but noticing when you just do Pascal's triangle, or at least once you notice it, or once someone points it out to you, the pattern is kind of obvious. So add these up, you get 1, 2, 4, 8. This, if you add these up, you get 10 and 8 is 18. Add these up, you get 32. So something is going on here. All right, we kind of discussed this already in a certain sense. So maybe you already have some kind of understanding of this. But I think the best way to understand this is to not look at this version of Pascal's triangle, but to look at the kind of unsimplified version of Pascal's triangle, because what is Pascal's triangle really? It's the triangle in which you first ask what are the number of ways of choosing 0 objects from a set of 0 objects. There's one way to do that. How many ways are there to choose no objects from a set of 1 object? There's one way to choose no objects, and there's one way to choose 1 object. And how many ways are there? So okay, I'll just keep writing this. 2 choose 0, 2 choose 1, 2 choose 2, etc. 3 choose 0. Okay, so this is like the real Pascal's triangle, and now we're starting to see what really is supposed to be shown here. The kind of theorem is, if you want to state this theorem more generally, the theorem is that if you go out to the nth row, well, basically just what is the nth row of Pascal's triangle, you might ask? It's n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 all the way out to n choose n. And supposedly this is 2 to the n. Okay, so this is the theorem that we are really proving when someone says prove that the sum of the numbers in the nth row of Pascal's triangle is 2 to the n. Never mind the triangle necessarily. The triangle is just a way of referring to the fact that we're summing up all of these binomial coefficients. Okay, well there are two approaches you can take here. So method number 1, which is what your book tells you to do in a little hint, which perhaps makes this problem, just not hard or something. And what your book tells you to do is, let me get their phrase exactly, consider the fact that, okay, this is so silly. They say, okay, hey, by the way, have you ever noticed that 2 to the n is really just 1 plus 1 to the n? Okay, well, of course that's true. Why is this relevant or helpful? Well, because what we can do is we can just take 1 plus 1 to the n, and we can just expand it kind of mindlessly using the binomial formula. What is the binomial formula in its full general form? Well, it says, okay, the first number in the expansion is going to be n choose 0 times 1 to the n times 1 to the 0. Plus, the next number is n choose 1 times 1 to the n minus 1 times 1 to the 1. And the next term will be n choose 2 times 1 to the n minus 2, 1 to the 2. And we keep going out until we eventually get n choose n times 1 to the 0 times 1 to the n. And all of this is 2 to the n because, 1 plus 1 is just 2. Okay, but of course all those numbers are just 1s, and now we are just done. So that's n choose 0 plus n choose 1 plus n choose 2 plus all the way out to n choose n. That is indeed 2 to the n. And therefore, I'm done with the problem, but I'm left with an empty feeling inside because I don't actually understand anything that happened. I'm just kind of plugging things into formulas and things are happening, and there it is. Okay, so method number 2 is to do a real, actual combinatorial proof. And I mentioned this 1 or 2 times, I'll mention it just one more time. What is a combinatorial proof? A combinatorial proof is a proof of a combinatorial fact, which just uses the definitions of the combinatorially defined symbols. Okay, in other words, what is n choose 0? It really is the number of ways of choosing 0 objects from a set of n objects. What is n choose 1? It's the number of ways of choosing 1 object from a set of n objects. And this is the number of ways of choosing 2 objects, etc. So let's actually invoke the meaning of these symbols to argue that this is 2 to the n. Okay, and the way you do this is you just tell a story. You explain why this is true. Okay, let's go. Suppose you are having a birthday party. And so suppose you have n friends. And now there is you have n friends. There's no restriction on the number of friends that you invite to the party. And you could invite all your friends. You could invite just some of your friends. And the question is, how many possible birthday parties are there? How many possible parties are there? Okay, I claim that both sides of this formula that we're trying to prove count the answer to this question in 2 different ways. And therefore they're equal, because they both count the same thing. Okay, so what's happening on the left? On the left, we're imagining the situation in which you first kind of worry about how many people you could invite to your party, and then you decide how many to pick. So I don't know, what kind of party should this be? This is like if you're going to have a wedding. Do you invite every single person in the whole village, or do you invite just your 5 closest relatives or something? This is a big decision. Well, let's see. I could invite no people to my party. That sounds like a great party. You just make a cake and you just eat it all by yourself. So, and if you're going to invite 0 out of your n friends, how many ways are there to do that? Well, there are n choose 0 ways to do that. There's one way to have a party with no people. It's like a COVID party. You just make a phone call, you send a couple texts, and you just stay home by yourself. Okay, how about if you decide that you want your party to be one person? Ooh, that's called a date. How many ways are there to pick just one person? Well, there are n choose one ways if you have n friends. Okay, what if you're going to invite just two people? That's a very intimate party as well. Well, if you have n friends and you decide you want to invite just two people, then there are n choose two ways to invite two people. There are n choose three ways to invite three people. And so if I'm adding up all of these different binomial coefficients, what I'm really doing is I'm calculating all the possible different kinds of parties, one at a time based on the size of the party. This is the number of parties of size 0, this is the number of parties of size 1, this is the number of parties of size 2, number of parties of size 3, etc. All the way up to the number of parties of size n. But that's all the kinds of possible parties. The party size must be somewhere between 0 and n because you have n friends. Therefore, the left-hand side counts the number of possible parties. But the right-hand side also counts the number of possible parties because you have n friends. So a more reasonable way, perhaps, to decide who to invite to your party is to just go through each friend and say to friend 1, do I invite you or no? 2 choices. Well, regardless of what choice I made, I now go to friend 2. How many choices do I have? Well, 2 choices, etc., etc. And so you have 2 choices for each of your friends, invite or not. Therefore, if I have n friends, and I want to count the number of different possible parties, the number of different subsets, essentially, of friends, then that's just going to be 2 to the n, because I've made n times, I've multiplied by 2, corresponding to the binary choice of whether to invite that person or not. Okay, so now what we have, hopefully, is via this method number 2, is not just a proof of this formula, but a deep understanding of what this formula really kind of means. Alright, if you like this sort of thing, then you should take discrete math, potentially even next year. Okay, goodbye!